Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Dermot O'Shea, and this is going to be more of an applied talk than most of the others we've heard today. I'm also more of a messenger. That this is reporting on work that's been going on over a few years, both at the Dialog Systems Group at the engineering department, and also now at Vocal IQ, which is a startup based in Cambridge. And generally, it's about dialogue systems and using neural networks to track what people are talking about when they're having a conversation with a computer. So, a dialogue system is a kind of essentially a kind of voice interface for a computer application, and whereas most voice-based interfaces that are out there at the moment are kind of one-shot interfaces where you say something and hopefully the computer goes off and does something if it's understood you correctly. In a dialogue-based interface, the idea is that it's more of a collaborative process, that you say something, the computer tries to work out what you want, maybe it makes some suggestions, maybe asks for more information, and together you kind of hopefully achieve some goal, which is that the computer does what you want it to do. So this is just an example of a dialogue system which is set up to help people find restaurants in Cambridge. And the user starts off with a vague goal that they might want to get Chinese food. The computer says, well, we've got a couple of Chinese restaurants. Let's try and work out exactly what Chinese restaurant suits your goal. Initially, the user says, I don't care about how much it costs. System makes a statement, then the user kind of remembers that left a wallet, they've only got £10 in their bank account or something, says, actually, oh, I need something cheap. The user says, okay, it makes some sort of update of what they think the user wants, and then eventually comes up with a suggestion that seems to be implicitly accepted by the user, and then the user can kind of ask for a telephone number or the website or something. And there's a couple of things going on here. Obviously, it's a natural language understanding problem. We assume that there's some underlying database that the system is able to query, but it needs to be able to work out, well, how to map language onto a query. It's got to be aware of the context. The user says, I don't care. Well, what does the user not care about? It's got to be able to, or what's the telephone number? It's obvious to us that, well, it's the telephone number for North China dumpling, but the system has to have some sort of context awareness. And it's also got to be able to update beliefs in a reliable way. Initially, the user doesn't care about how much it costs, but then changes his mind. So this is kind of the kind of data we're going to deal with in this talk, and kind of application we have in mind. So this is kind of a standard slide that appears in most talks about dialogue systems, which is the top level view of here are all the different components. The user inputs by talking to the system. That has to go through speech recognition. Then the speech recognizer passes on. So the speech recognizer is uncertain about what the user has said. So it's got a number of hypotheses, which it's assigned probabilities. Then what people in the speech community call, or in the dialogue community call dialogue state tracking. In the NLP community, it might be called kind of semantic parsing or semantic interpretation. That's what this talk is going to be about mostly. But then there are other components. Once the system has decided this is what the user wants, the dialogue manager has to decide what to do next. So if it knows, and it can also talk to to this underlying ontology or knowledge base or database, which is, so the dialogue manager might receive the information that the user is looking for a Chinese restaurant, and then it goes and asks the ontology, well, do we have any Chinese restaurants? And based on that, it's going to decide what to do next. So it might find, well, there are 5 Chinese restaurants. Some of them are expensive and some of them are cheap. So then it decides, okay, let's find out what price range the user cares about. So it kind of comes up with a schematic description of what the response should be. Then that has to be converted back into natural language, and then that has to be converted into kind of an output speech signal. So as I said, today I'm just going to be talking about this dialog state tracking component. So the way we conceptualize the problem is that we have on the left, we're just going to run through incrementally run through the utterances that the user says, and then the right, we're going to keep track of our belief about what the user actually means. And in reality, well, this is going to be kind of the gold standard ground truth labeling. In a real life system, we are never certain, and we have to maintain a distribution over the state of all possible interpretations. So the user starts, I want to get Chinese food, and this is annotated as the user is informing that it's kind of we use these slot value pairs where there's a food slot and it's filled by the value Chinese. System says something back. Then the user says, I don't care, and by looking at the dialog, we know that this means that the user is saying that it doesn't care that they don't care about price. System makes an offer. User changes his mind, so at this point we have to update the representation of the belief. System makes an offer, and then the user makes a request of the phone number. So the task is the task that we're trying to learn to do is to map from an utterance in a certain position in the dialogue to this state representation at any point. And in this talk, we're just going to assume that the state consists of informs, which are basically constraints on slot values. So for each slot, we have a distribution over all the possible values for that slot. So kind of a categorical distribution. And for each of the attributes in the database, they're either requested or they're not. So you could when I get to talking about the data, yep.
How about state that's added by the system? So in the dialog here, the system talks about a concrete restaurant, but it doesn't seem to be reflected in your state.
Yeah, that's kind of an assumption of the state representation. In the dialog state tracking, we only try to interpret what the user says, but obviously in the dialog manager, it knows that an offer has been made, and that's going to help it. And those, as we'll see, knowledge about what the system has said is also useful as features for predicting what it is that the user has said. There we go. So what makes it so? People have been working on this problem for a long time. There are lots of proposals out there for how to build a dialogue system. So there are just some ideas about what would be useful what are the useful desiderata for a robust, deployable state tracker. So to be realistically useful in a deployed application, it's got to be incremental. We've got to be able to update the belief state after each utterance. We can't just do kind of batch prediction. Obviously, to interpret properly, we need to have some awareness of the dialogue context. We'd like a model that's trainable. It's not given more data, we can improve performance. And ideally, we would like something that is as portable as possible, that's not tied to a specific ontology, that can possibly it can adapt quite easily if the ontology grows, but also maybe something that we could take out of one application and put in another application. So the idea that that we're going to talk about in this talk, which it's not the only way you could do this, but it seems to be a reasonable way, is to treat a dialogue as a sequence of turns. So essentially, it's a kind of sequence labeling problem with a slightly structured space for the labels. And pick your favorite sequence labeler, but one idea is to use recurrent neural networks. And the idea is, this is kind of a simple neural network with a single hidden layer. And the idea is, at each turn, we take in input, which essentially input layer consisting of some features. We learn to map that onto a hidden layer, and then we learn to map that hidden layer onto there are two components in the output space. One is the belief state, which is essentially a probability distribution over beliefs about what the user is looking for. And then for convenience, we also have what we're calling a memory, which is just a vector of real numbers, which is only for the consumption of the system. It doesn't have any interpretation outside the system, but it allows it to store some information about what's going on. And as a recurrent network, at each turn, apart from the first, we take in the output components of the previous turn as essentially as features. And what are those features? First few are pretty simple. We've got some features about what the system has just asked or said. If the system has just said, here's a really good restaurant, it's called 7 Days, then we want to encode that as a feature. If the system has said has asked what price range the user is looking for, then that's another kind of useful feature. Then kind of very standard things you'd expect. We extract n-grams, again, because we are dealing with speech recognition where there is uncertainty about what the user says. We have to weight these n-grams by the probability assigned by the ASR to the sequences they appear in. So if it's I want Chinese food, here are some n-grams you might expect. Maybe the user didn't say China's food, but it appeared in one of the ASR hypotheses. And then we have an idea of tagging, which is essentially looking up the ontology for strings which match onto entities or attributes. So for the purpose of this talk, we're just going to assume we're doing exact string matching. Obviously, people don't always use the exact name of an entity to refer to it. So here we have in the first tagged n-gram, we've taken the n-gram want Chinese food and pointed out that, well, we know that Chinese is a value for the slot food, and we know that food is the name of the slot food. And then you run through all possible taggings to extract these tagged n-grams. And then, as I said before, we are maybe interested in portability or domain adaptation. And so then it can be useful to extract delexicalized features, which essentially say, the intuition here is that something, if I say I want X, and we know that X is something in our ontology, then that's a pretty clear signal regardless of what X is. Putting all together, this is essentially just putting down in equations what was shown in the neural network schematic. There's some kind of sigmoid nonlinearity in the hidden layer, but apart from that, it's all pretty straightforward. Except we have two models. One is just based on, these delexicalized features for a given slot. So if we take an utterance and we check whether it contains any terms that appear in our ontology, we want to assign that tag a score, and that can be done without actually caring what the tag is. And that's done in the first model. And in the second model, we actually say, well, we're just going to feed in. We're just going to map the entire input into a hidden layer, and then we're going to learn a mapping from the hidden layer to all possible values. So if there are 3 different price ranges, then we learn 3 sets of mappings from the hidden layer to the output layer. And those parameters are specific to a fixed ontology, so not so portable, but they do give better performance when you know exactly when you're able to train on the ontology, on the application that you know you're going to be testing on. As I said before, the states contain kind of goals, which are distribution over values for a slot, and so we do a sigmoid transformation of the scores for that, or softmax for that, and the requests are essentially binary elements of the state. Did they ask for the postcode? Did they ask for the telephone number? Did they ask for the address? The data used in experiments come from what's called the Dialog state tracking challenge. There's about 3,000 dialogues in the data set, which were collected from through Mechanical Turk, again, in this idea of having a restaurant information system for Cambridge. And there are 4 kinds of goals the user might be looking for. It can ask for specific food, specific price range, specific area, specific name. And then there are a couple of other attributes which they can request information about. Matt Henderson, who was a PhD student at the engineering department, is hosting the data for that. Training, standard kind of setup for training a neural network, static gradient descent. We do L2 regularization on the parameters. The training proceeds in 4 stages. One to kind of an unsupervised stage using a denoising autoencoder. Then there is a shared initialization which uses the delexicalized features to train a single model for all slots. So it's a kind of a slot agnostic model. So this is something that you could plug in anywhere. And then you specialize it by learning specific sets of parameters for each slot in the ontology, and then you can learn the fully lexicalized model, which encodes the exact set of values in the output space. And random initialization and so on. So all the results are averaged over 12 runs. The baseline from the DSTC challenge is the blue bar. It's the tough. They had a couple of baselines. This is the toughest baseline. It's pretty, not quite state of the art, but a pretty good system. And on the left, we have accuracy. Higher is better. On the right, we have a kind of an L2 distance between the true labeling, which is kind of a peaky distribution, and the probability distribution produced by the tracker. It's in Matt's paper. Yeah, as you can see, we're doing pretty well. We were, I think, at the L2 metric, it was the best in the competition, and it was second best on accuracy. Thanks for listening. As I said, lots of people involved.
I have a question. Why not a GP? Sorry to answer.
As I said, it's in a sense it's just a sequence labeling problem with a structured output space. So you could pick your favorite algorithm. I guess some sort of inertia. They work well. I mean,
Real questions? Okay, so thank you very much.
Thanks.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.